The Commodore 64 contains a marvelous sound chip called the SID, and there's a vibrant community of people who make SID music using specialized Commodore 64 music editing software. Some use tools like Goat Tracker or Cheese Cutter that run on modern computers and emulate the SID chip, whereas others prefer native tools like Blackbird or SID Wizard that run on the C64 itself. But in order to use one of those tools, you first have to get the software into the machine by loading it from floppy disk, tape or cartridge. But suppose you haven't got any of those peripherals. Suppose all you have is a stock unexpanded bread bin and a display with speakers. Well, in that case, you're stuck with a built-in BASIC interpreter. BASIC, of course, is the beginner's all-purpose symbolic instruction code. It's been marketed as a powerful programming language that's very easy to use, and I'll let you be the judge of that. But here's the thing, the BASIC dialect that's bundled with the C64 is rather limited, and in particular there are no built-in commands for producing sound. So I thought it would be a nice challenge to try and make a chiptune using nothing but the built-in BASIC. Now, this video is going to get absurdly technical, but don't panic. You can try to keep up if you want to, but that's really not the point of the video. My purpose is to entertain you and broaden your horizons with a style of recreational programming that's probably unlike anything you've ever seen before. So with that in mind, please follow me down the rabbit hole that is making music from scratch at the BASIC prompt. Before we start, I'd like to give a special shout out to Walt of Bonsai, who showed me the ropes of live coding on an unexpanded C64. I've developed the technique and added my own little twists, but I'm definitely standing on the shoulders of a giant here. So thank you, Anos. And so we begin. As I mentioned, C64 BASIC has no built-in commands related to sound, but it does provide a very sharp tool called poke that lets us write data to arbitrary memory locations. The address space of the C64 is organized into pages of 256 bytes. For instance, the video memory starts on page 4, and the first byte, which is then at address 4 times 256, represents the character in the top left corner of the screen. So if we poke the number 1, which is the screen code for capital letter A, to that location, an A instantly appears in the top left corner. Most of the address space contains regular memory, but some pages contain hardware registers instead. So for instance, page 208 controls the video chip, and register 32 in that page sets the border color. Let's pick green, which has color code 5. If we hold stop and hit the restore key, it means stop the current program and restore the hardware registers. Poking manually is tedious, so we're going to write a BASIC program to do it for us. We're going to read from a table, and if the value was non-negative, then we're going to poke it to some address A, then we're going to increment the address, and then we're going to jump back. However, if it was a negative number and it wasn't the special marker -1, then we're going to set the address. So we're going to flip the number back to positive and multiply it by 256, and that's going to be our new address. Then we jump back. Okay, that's the program. Now some data. Let's start on page 212. This is hardware registers for the SID chip. We have 7 registers for voice 1, 7 registers for voice 2, and then voice 3, and then we have 4 global registers, the last of which is the master volume from 0 to 15. At the very end of our program we put the special -1 token to stop the program. So if we run this, we're going to hear the characteristic click from turning on the SID chip. We can set a pitch and a volume envelope, and then we can enable a sawtooth waveform. And we have sound. Great, but we're also gonna need machine code. So let's move to a free RAM page. Page 192 and up are free. And we're gonna load the accumulator with the number 5. And then we're going to store the accumulator at offset 32 in page 208. So this is exactly the same poke that we did earlier, expressed in machine code. At the end of our routine, we're going to return from subroutine. So if we run this, our machine code is now on page 192, and we can call into it. And it sets the border color to green. So let's put the syscall into the program to automate everything. Now let's do something more useful. So instead of setting the border color, we're gonna inject some code into the system interrupts. So we're gonna first disable timer interrupts, and then we're gonna put a pointer to our code. It's gonna be at the start of a page. We put the pointer in page 3, there's a vector there, and then we need the upper byte of our code. It's going to be on the next page, page 193. And then we also need to re-enable the timer interrupts when we're done. Okay, and before we run this, we have to put some code on page 193 that's going to execute as part of the interrupt handler. And for now, we'll just set the border color to 1, which is white. And then at the end of our interrupt routine, we set it back to light blue, 14. Then instead of just returning, we're supposed to jump back through the default interrupt handler code, which is handling cursor blink and keyboard scanning. So what was the pointer originally? 49, 234. So we put 49, 234. This is an address into ROM. And if we now run this, we're gonna see our code running as part of the interrupt handler. And it's running a little bit all over the place because the timer interrupt is not synchronized to the video beam. So instead of re-enabling timer interrupts, we can actually enable raster interrupts in the video chip. That's done with register 26. And the default location of these raster interrupts is off screen, so we're going to put it somewhere else where we can see it. Now the code is running all over the place. This is because we are not acknowledging the raster interrupts. So as part of our interrupt handler, while we conveniently have a 1 in the accumulator, we can store it to register 25 in the video chip to acknowledge the interrupts. Now it should run once per frame. And there we have it. Notice that the sound started before the visual indication. This is because BASIC is starting the sound, and then it needs to churn through a lot of numbers before actually calling the machine code. So let's move that. Let's have some machine code to enable the sound instead. So on line 250, we will load 33 and store it at offset 4 in the sound chip. Now they start at the same time. Speaking of interrupts, let's take a little break and recap. So I've written a small BASIC program to read data from a table and populate registers and memory. And then a machine code routine that installs an interrupt handler and plays a simple static sound. But in order to play a melody, I want the pitch of the sound to change over time. So the interrupt handler needs to keep track of time, and I could do that by incrementing a variable inside the interrupt handler. But I happen to know a shortcut. The default system interrupt code is conveniently incrementing a variable that we can read. It's at offset 162 on the 0 page. If we just store that into the upper byte of the pitch register, then we get a rising pitch. Now this value is incrementing rather quickly, so let's divide it by 8 by shifting to the right 3 times. So now it goes from 0 to 31. And this is an overtone series. But if we instead want a chromatic scale, Then we're going to need to compute the pitch table. For that we need floating point math, so we're going to resort to basic. We're going to compute 1 page worth of entries, or actually 2 pages. So on page 194, we're going to store the low byte of f, and then on page 195 we're going to store the high byte of f. Then we're going to increment f by a semitone, which is the 12th root of 2, and that's, I happen to know, 1.0595. So if we run this, BASIC is going to compute all the pitches for us. And BASIC is slow, as you all know. And it crashes on line 40. What's going on there? What's F? F has just overflowed the signed 16-bit range. This happened on note 117. Now there are workarounds for this bug, of course, but I don't think we need that many notes really, so we'll stop just before the crash. Waiting for the pre-calc again. And if this works, we're gonna have... Yeah, I guess we do have a table of chromatic pitches, but we're not using the table yet. So let me see. Yes, so instead of just computing this counter from 0 to 31 and storing it into the pitch register, we're going to transfer it to the Y register, and then we're going to do an indexed lookup. So we're going to read from an address plus contents of register Y. So we're going to read from our table of low bytes, and then we're going to store into the low byte of the pitch register, and then we're going to read from the table of high bytes and store into the high byte of the pitch register. And if we try this, right, BASIC is pre-calcing again. The thing is, though, that all of those numbers are still in memory, so we're never gonna need to pre-calc them again. That's the whole point of memory, right? And now I think it's actually working, but it's using the 32 lowest numbers in the table. Let's read, instead of reading from the start of the page, we're going to read from somewhere in the middle. Yeah, it's a chromatic scale. So I've been using the counter directly as a note value, and the next step is to use the counter as an index into a table of note values, a melody table. It would be possible to define such a note table using ordinary data statements, but when you're working creatively with music, it's enormously helpful to have a quick turnaround time, so you can make changes and experiment and immediately hear the difference. So at this point, I'll start to make an interactive tool. Since the play routine keeps running in interrupt context, I can build my makeshift music editor on top of the interactive BASIC environment. The melody tables will be part of the screen buffer, but I'll make a template for the screen buffer inside the program using rem statements, which are comments. I'm going to draw a user interface inside the BASIC listing. 1, 2, 3, 4, 5, 6, 7, 8. And then below that, some grid graphics for the first voice, second voice, and third voice. Then let's put some blank lines that we're going to use in a minute. Yeah, so now you see the interface inside the BASIC listing. This here is going to be the timeline, and this is going to be like a piano roll where we put notes using letters of the alphabet. And in order for me to remember which letter corresponds to which note, I'm drawing a little piano keyboard in alphabetical order here. So in the user interface, this is just decoration, but a very helpful decoration. W, X, Y, and Z. Return, return. So if we list from the top of the screen, if we list these lines, we get the user interface on the screen. So let's do that as part of the basic program. So we're gonna clear the screen and then list 80 to 89. The problem is that if we run this, we get the user interface on the screen, but we don't hear anything. And that's because list was never intended to be called from within a program, because it always drops us back to the ready prompt. So we can use it at the very end of the program. Right, 0, 40, 80, 1, 2, 3, 4, 5, 6, 7. The time axis begins at position 87 in the screen buffer. Let's animate it. So here we have the current song position in the Y register. Let's load 1 for white and store that indexed by the Y register to position 87, not in the screen buffer, but in color RAM. Okay, now we need to clean up behind us. So before we put the white, we're gonna put light blue one step to the left. Yeah, this is gonna mess up in the rightmost column. So let's always put light blue in that column. 86 plus 32, 118. Now it should work also in the final position. Yeah. So far, all the sound generating code I wrote operates on the first voice of the SID chip, but I want to do the same thing with the other two voices. The functionality is going to get increasingly complex, and I don't want to maintain 3 slightly different copies of the same code, so this calls for abstraction. And one way to abstract is to break out common functionality into a subroutine. So it's time to create a subroutine to handle all the stuff that we need to do for each of the 3 voices. So we're going to put our subroutine on a fresh page. 196 is free. And let's move the note lookup into this subroutine instead of having it here. And then at the end we're going to need a return from subroutine instruction. Okay, let's call the subroutine. Actually, first we're going to need to read. We have the song position in the Y register, so we're going to read indexed by Y. Not from position 87, which is the time axis, but below that, 127. And not from color RAM this time, but from the screen buffer. And this will pick up the screen code from the grid line. Then we're going to call the subroutine on page 196. And the first thing we're going to do in the subroutine is to transfer this screen code into the Y register. Right, so it's picking up note values, but it's also treating space and colon as notes. So the very first thing we do in the subroutine is going to be to compare the note value against 32. If it's less, then it's a letter. Then we're going to skip 3 bytes, otherwise we're going to jump to the next page. So for colon and space we jump here, and for now we don't do anything here. And we can remove the static initial pitch. Seems to work. But of course it only works for the first voice, because we hard-coded everything for the first voice. So let's add a parameter to our subroutine, which is going to be in the X register, and it's going to be which voice we're dealing with. So load X 0, and then we're gonna, when we store into the sound chip, we're gonna add X. So that's gonna be our register offset. It's gonna be 0, 7, or 14. And we're gonna read also the second line of the grid and the third line. And we're also gonna call the subroutine 3 times in total. So what do we have? And of course the accumulator gets overwritten, so we have to store it somewhere. I'm going to push it to the stack. And that means we have to call the subroutine in the reverse order. So offset 14, then offset 7. And here we also need to pop the value back from the stack. Right, now it should deal with pitches on all 3 grid lines. But it doesn't. And that's because we are not initializing the volume envelope for those voices. But also I think we're only initializing the waveform on the first channel. So let's move this into our subroutine and also add X to the target address. And then we take away the old line. Let's see if it works. We have polyphony. Let's also do something in the note off routine. So if we are enabling the waveform here, we might as well disable it in the note off routine. Whenever I restart the program, an empty grid is transferred from the program listing to the screen buffer. But the beauty of using list to draw the user interface is that I can now press return to save an individual grid line back into the program, so it'll be there when the program restarts. If I make a mistake when editing the screen buffer and I want to revert to the saved version, I could restart the program, but it'll be quicker to just relist the grid lines. If I list 80 to 89 here, that will revert the grid to the way it was in the program. And that's quite handy to have at the top of the screen, so let's make it a permanent part of the user interface. List 80 to 89. That way, if I mess up, I can just hit home and return and get the grid back the way it was. Oh, that's bad. Let's home return. Now let's put in some actual music. This is a pretty standard idiomatic bass line, but now I'll try to improvise a little melody. I'm not quite happy with the last bar. That'll do. Let's add some treble on top. With a subroutine, I give all three voices exactly the same treatment. But that results in a rather bland overall sound. And I decided that I want more variation. Each voice should play a different instrument. But I still want to reuse the same code for every voice. So the differences will have to be in the form of data rather than code. In my subroutine, I use the X register to tell the voices apart, and X is 0, 7 or 14. So this data should be organized in chunks of 7 bytes. Now let's have some parameters to differentiate the three voices. I'm going to put them on a new page. And we're going to have 1, 2, 3, 4, 5, 6, 7 bytes of data per voice. And the first of those bytes is going to be the offset in the pitch table. So the middle voice can stay at 70, the top voice can be an octave higher, and the bottom voice can be 2 octaves lower, 46. And then before we transfer the screen code to the Y register, let's see, carry is already clear. We were going to then add, indexed by X, what's in the parameter table. 8. And then of course we should not add 70 again here. It's a big difference, but we can make it even bigger by differentiating also the volume envelope. So the top voice can have really long notes, the bottom voice can have a little longer notes, but then we should also compensate for the envelope bug in the zip chip. It's good, but it's only sawtooth waves. So let's also put in the waveform numbers here. We're keeping sawtooth waves for the bottom voice, but in the middle voice we're going for pulse waves instead. And for the top voice we can have triangle waves. And then of course we should not hard code, we should load 1 byte into our parameter table plus X, and here we're going to load at 2 plus X from our table. Okay. And something is wrong with the pulse wave. Yes. We're still at 0 pulse width. So I'm going to change that. Good. Now for the bass part we could do with some percussion. And we can cunningly switch to a noise waveform when turning off the bass notes. The noise burst is there, but it's low pitched because it inherits the pitch from the recent bass note. So whenever I switch to the noise waveform, I also want to select a higher pitch. Now the control byte for the noise waveform is 128, so it has the most significant bit set and can be interpreted as a negative number. Therefore, loading the noise waveform byte sets the negative flag in the processor status register, and I decide to branch on this flag to handle the special case. And with that final code tweak in place, I'm ready to jam. In the note off routine, we can detect that we are dealing with a noise waveform. If not, we skip 3 bytes. Otherwise, we store that number, 128, also into the high byte of the pitch register. And this gives nice high-pitched drum sounds. And that's how you make music from scratch at the basic prompt. Thanks for watching all the way, take care and keep up with the Commodore.